to move in that circle. So the string is providing the centripetal force, and that's giving the ball its acceleration that is centripetal, directed towards the center in that case. Yes?
Can you explain what the black body and the black body spectrum is a bit more?
So a black body is a hypothetical object that would be a perfect emitter and absorber of radiation. And by that we mean, by perfect absorber, we mean that all the light that fell on the black body would be absorbed on it. It would not reflect anything. Not even one photon would be reflected from its surface. Every photon that hits the black body, it eats it. It absorbs it. That's where the name comes from, because at low temperatures, a black body would look as black could be. I mean, it would be like looking at a black, it wouldn't be a black hole, but it might as well be in terms of looking at it, because you wouldn't be getting any light whatsoever from it. On the other hand, black bodies don't just absorb radiation, they also emit radiation. And if the temperature is high enough, then you can see the light by which the black body is glowing. If the temperature is too low, it's still glowing, it's just at wavelengths our eyes can't see. It would be glowing at radio or infrared wavelengths rather than visible wavelengths. And the black body spectrum is the mathematical form of how much light comes out at each wavelength for a black body, for something that is this hypothetical perfect emitter and absorber of radiation. So essentially, we're not writing down the mathematical formula. It's slightly complicated. It's not horrible, but it's a little bit of a complicated formula involving an exponential. But the shape of it, plotted on this logarithmic, what's called a semi-log plot here, where the intensity is plotted so that equal spacing on the axis is equal powers of 10, and then also the wavelength is plotted the same way. Sorry, so it's not semi-log, it's sort of a log-log plot. Both axes are logarithmic. The shape of it looks like this. It rises up to a peak wavelength, and the wavelength of the peak comes from Wien's law. And on either side of the peak, the amount of light that the black body gives off is smaller. So the black body spectrum is, any of these curves is a black body spectrum. It's the plot of brightness versus wavelength for a given temperature of the black body is its spectrum for that particular temperature. No real objects are black bodies, but things can be good approximations to black bodies under various conditions. So a star is definitely not a black body, but the spectrum looks like this, except there's lots of absorption lines, and it doesn't quite have exactly that shape, but it's close. So things can be decent approximations to black bodies. The cosmic microwave background radiation is an extremely good approximation to a black body, it turns out, in terms of its spectrum. So does anybody have an exam after the astronomy? You still have one after this one tomorrow? That's terrible. That sucks.
Yeah.
So in other words, you've probably been watching people kicking back, saying, oh, my exams are done, and you got two on the last day. That used to happen to me all the time. I feel your pain. Yes?
So is the exam going to be like more focused on the last couple chapters we've read?
There is some emphasis on the later chapters that we have not been tested on. I don't remember exactly what the division is, but there's definitely additional emphasis on the chapters that we've covered since the last exam, since exam 2, yes.
Can you review stellar
Stellar parallax, how we determine distances to stars. It's the only direct way we have to measure star distances. We can measure distances in our solar system using radar. We can bounce radar off of planets and measure precisely how far away they are from us. But with stars, they're too far away for us to use radar. And so we have to use a more indirect way. Well, it's direct, but it's trickier than using radar on some level. Anyway, what's the chapter number on that?
15.
15. Okay. Did I already bring up 15 as the next? There's too many things to try to. Okay, here we go. All right. So, whoops. Let me escape out of there. And yeah, stop that. Bring up the picture. Yeah. So the idea with parallax is you use parallax all the time without thinking about it. Your brain does. That's why you've got two eyes. Your eyes have slightly different points of view to anything that you're looking at. So the way your depth perception works is, for example, if you hold your thumb out in front of your eyes, your left eye sees a different background behind your thumb than your right eye does, because if you draw a line from your left eye to your thumb versus a line from your right eye to your thumb's in front of different things for your two eyes. And your brain, without you even thinking about it, uses that to calculate how far away your thumb is and make it look like it's hovering out in space in front of you. That's how depth perception works. Pretty amazing. Stars are too far away for our eyes to be able to tell the difference in their point of view, because stars are light years away. So we need something that's further apart than our eyes, and what we use are different, we're riding on spaceship Earth, and so it's a platform that we can use to make a baseline. So in other words, here's Earth today, 6 months from now, here's Earth halfway around its orbit, and the idea then is that for stars that are near enough to us, we can actually measure the difference in perspective to that star from different points in Earth's orbit. If we draw a line from Earth to the star today versus Earth to the star 6 months from now, that nearby star will appear in front of different faraway stars because of that shift in perspective, the line of sight. And this is not to scale. Stars are hundreds of thousands or more AU away. So these stars should be way, like several 100,000 times or more AU, much further away than this, but then we wouldn't be able to show what's going on. The idea is the shift, just like your thumb in front of your eye, the shift is bigger the closer your thumb gets to your eye. The shift is bigger the closer a star is to Earth. And so we can use how much a star shifts back and forth, making precision measurements, how much it moves back and forth on the sky over the course of the year. That's half of that amount that it shifts back and forth. It's called its parallax. We can use that to find its distance. That's the idea behind parallax. And there's a simple formula because we define the parsec to be the distance at which the parallax is 1 second of arc. And so then, because a bigger parallax is a smaller distance, it must be in the denominator. The distance in parsecs is just 1 divided by the parallax in arc seconds, is what it comes down to. So the further away the star is, the smaller is its parallax, and vice versa. If the star's parallax was 0.1 arc seconds, then it would be 1 over 0.1 equals 10 parsecs away from us, for example. Plugging into the formula there. So, does that do it for you? Or does anybody have further questions about that? Yeah. Okay. I gotta say, I'm definitely getting the vibe from you guys of like, I had all these exams, I just have this other one to go. Unless life really sucks for you and then you have 2 more to go. But the rest of you are like, I still have another exam to go. Oh my God. Trust me, I did not set the time for these. Not what I would have chosen. One, it's on the last day. Two, it's at friggin' 8:30 in the morning. Neither of those things would I have approved, but it's not up to me. Oh no, Johnny, now you're gonna get me going. Yes,
So back to the dark energy.
yeah.
Does that satisfy the concept that energy can't be created or destroyed? Because like based on-
Strangely enough, it does not.
because
yes.
there has to be an additional force that is explaining that, like going faster.
So it's weird because the thing is, so if dark energy really is an energy associated with empty space, here's the thing. The universe is expanding. Space is continuously being created, and every cubic meter of space has this dark energy in it. So that means that the amount of dark energy in the universe keeps increasing. Where does it come from? Here's the weird thing. I know it's been drilled into your head that energy is conserved, it can be neither created or destroyed, and all that. That doesn't apply to the dark energy, believe it or not. Dark energy is not conserved. More of it just keeps getting created. It doesn't obey energy conservation. The technical reason for that, and this is probably not going to help, but for energy to be conserved, it turns out that there's this quantity called the Hamiltonian that is used to describe a system. And you can derive the laws of physics from the Hamiltonian, and if the Hamiltonian doesn't depend on time, then energy will be conserved. But if it does depend on time, energy will not be conserved. And it turns out when you throw in the dark energy, the Hamiltonian of the universe depends on time because of that, which kind of makes sense. The universe is changing over time. But it turns out that no, energy is conserved locally in the universe, but not globally. The total amount of energy in the universe is actually increasing because of the dark energy. And there's a flip side to that, which is as the universe expands, the photons are getting stretched out and losing energy. And that's another example. The energy in the cosmic microwave background is decreasing because the redshift is robbing the photons of energy. The energy in starlight coming to us from distant galaxies is continuously decreasing because those are being stretched by the expansion of the universe. Does that violate energy conservation? Yes, it does. That energy isn't going anywhere, it's just disappearing and not being replaced. So in other words, we've got one type of energy, the energy in photons and so forth, that is just disappearing over time. It's decreasing over time. And this other form of energy, which is bigger, the dark energy, which is increasing over time, and neither one of those is conserved. It violates energy conservation. Energy conservation is a local thing, not a global thing. That's a great question, though. It's a very tricky point.
But we don't have to know any of that.
Oh, I'm going to ask you a big essay question about it.
It's bonus.
Yes, that's the bonus, yes. 500-point bonus, yes. Mhm. No, but I do think it's an interesting fact to realize that. Yes?
What's like the main thing we should know about the proton chain? Because I feel like there's like a lot of information with that.
Proton chain, I just want you to know, first of all, what the net reaction is. So how many hydrogens form a helium nucleus? How many hydrogens go into forming a helium? Crickets. Chirp, 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 chirp. So 6 go in, but what comes out at the end along with the helium? 2 protons. So what's the net? 4 hydrogen form how many heliums? What was it? 1. Yeah, so 4 hydrogens form a helium, 4 nucleus, plus energy. So 4 1H's, protons, produce 1 helium-4 nucleus, 4 He, plus energy. Energy comes from the fact that the helium nucleus has less mass than the 4 hydrogens did that went into it, and that gets turned into energy. And the other thing I want you to understand is this idea that why does fusion require high temperatures? Why does fusion require high temperatures? What's keeping protons from just fusing in this room, which would suck because we wouldn't be here? The repulsion due to their electrical charges. You got to get them moving fast enough to overcome that. Remember that temperature can be thought of as a measure of how fast, what the average kinetic energies are of the particles. And so you need to have high enough temperatures for the protons to be moving fast enough to overcome their mutual repulsion. Why does helium fusion require a higher temperature than does hydrogen fusion? It's not more. It is more mass, but that's not why it requires a higher temperature per se. If I've got 2 heliums starting to collide, trying to collide with one another, they get a bigger repulsion. Why? Because a helium nucleus has how many protons in it? A helium nucleus. Periodic table. The first element is hydrogen. The second element is helium. So how many protons are in a helium nucleus? 2, because it's number 2 element, right? Yeah. So to fuse helium, you got to get things with 2 protons to collide with one another. That's more repulsion than 1 proton colliding with 1 proton. So you got to get more energy to overcome their repulsion, higher temperatures in order to overcome that repulsion. So in general terms, it's not a perfectly, it doesn't always work, but in general terms, the more protons that are in the nuclei, the higher the temperature you're going to need to get them to fuse with one another because there's more repulsion. It's more complicated than that, but that's the general rule, which is why a massive star, the core has to get hotter and hotter to undergo all those successive stages where more and more highly charged nuclei are fusing with one another. Yes?
What is an H2 region? And what causes the ionization of hydrogen within one? And gives it the pinkish color?
Yeah, so an H2 region, here's one right here. The pink glow from parts of the Trifid Nebula is due to emission from hydrogen atoms. An H2 region is also called an emission nebula because it's producing emission lines, which is what is giving it its color. It's emitting. It's an ionized. It's ionized gas. It's a plasma. It's mostly hydrogen. The reason it's called H Roman numeral 2 is, remember that we have this weird notation that astronomers use where H Roman numeral 1 is neutral hydrogen, just hydrogen atoms that have an electron. H Roman numeral 2 is you took the electron off. So an H2 region is a region where many of the protons are bare. They don't have an electron orbiting. They are bare hydrogen nuclei because the electron has been stripped off of them. They've been ionized. So what is providing the ultraviolet photons that are ionizing that gas? H2 regions, what's big picture? What's happening in an H2 region? They are stellar, starts with an N.
Nursery?
They're nurseries, yes. They're stellar nurseries, so stars are being born there. In particular, there are O and B type stars being born there, which have very high surface temperatures. They produce copious amounts of ultraviolet photons, many of which have enough energy to tear the electron off of a proton and ionize the hydrogen. So it's UV photons from the O and B stars inside the H2 region. They're these baby O and B stars that are born in the H2 region that ionizes them. And the reason that they glow, they give off emission lines, is that an electron which has been torn off of a proton can wander around and then find another proton that had its electron torn off of it, and they can reunite, recombine to form an atom again. Typically, the electron gets captured into some high energy orbital, and then it drops down to lower and lower energies, giving off emission line photons as it goes, and that's what we're seeing the glow from. It's photons coming from electrons dropping down in energy after they recombine with protons to form neutral atoms. So there's a constant balance between atoms being ionized by ultraviolet photons in an H2 region and electrons and protons recombining to form atoms again and giving off light as the electron drops to lower and lower energies in the newly formed atoms as it drops towards the ground state of the atom. Don't be afraid to ask a question if you have. Oh, good, good. Yeah. Because somebody would be like, yeah, I'll ask a question. And somebody would be like, I'll just listen to other people's questions. I don't want to ask. Yes?
I know we talked briefly about like what is the relationship between total density of matter and the energy in the universe with like the shapes?
Yeah, it's that whole shape thing. So it turns out, again, it's, you know, this should not be obvious to you. It's not obvious, but the geometry of the universe is understood via general relativity. Remember, according to general relativity, gravity is curvature of spacetime due to mass and energy. Mass and energy curve spacetime. That's what gravity is according to general relativity. Gravity doesn't cause curvature of spacetime. Gravity is curvature of spacetime due to the presence of mass and energy. And general relativity, the equations of general relativity, allow us to predict how space will be curved by mass within it. And in particular, if you have a universe and you spread mass uniformly within it. Now, of course, mass is not uniformly spread within our universe. There's concentrations of mass like people and stars and planets and galaxies and all that. But if you imagine spreading the mass out and energy too, because energy also curves space-time, because in relativity, mass and energy are equivalent to one another in some sense. So mass and energy curve space-time, and that curvature is gravity according to general relativity. The equations of general relativity allow you to predict what will be the geometry, the shape of the universe, depending on how much total mass and energy there is per unit volume within the universe. So there's what's called the critical density, and again, that works out to be equivalent to having on average, about the mass energy equivalent of about 5 hydrogen atoms per cubic meter in the universe. The critical density is what it would take to make the universe flat. Make the density any higher and the universe becomes spherical. Make it any lower and the universe would be saddle-shaped. And that's that relation, that there's a critical density for which the universe would be flat. Higher than that makes it spherical. Lower than that makes it saddle-shaped. Yes?
Can you go over how like Wien's law and the Stefan-Boltzmann law are related to the color and luminosity of stars?
So first, we should remind ourselves what's the deal with those two laws. So, trying to find the magic chapter here. Because I think I've already got it up. It's 5, yeah, okay. So, here again is the black body spectra for these black bodies with different temperatures. And there's two laws associated. So one is Wien's law is related to where the peak wavelength is. The peak wavelength, the wavelength for which the curve has its maximum value, at which you can think of it as being the wavelength at which the black body is brightest in its glowing. Wien's law describes that, and it says that if I know the peak wavelength of the black body, I can plug into this formula to find out what its temperature is. The temperature in Kelvin is 2.9 times 10 to the 6th power nanometer Kelvin divided by the peak wavelength. So if I know, if I were to measure the black body curve and find where its top is, so to speak, and figure out what wavelength that was, I could use that to figure out how hot the black body was. That's going to be related to the color, because if we look at these three different black bodies here, three different temperatures, 15,000 Kelvin star, the sun, which is 5,800 Kelvin, a 3,000 Kelvin star, their peak wavelengths are different. The hotter a star is, the shorter is the peak wavelength, which kind of makes sense, because what happens to energy of photons as you decrease the wavelength, does the energy of a photon go up or go down as you decrease the wavelength? What's got more energy, a blue photon or a red photon? Blue. Is blue shorter wavelength or longer wavelength? Shorter. So remember it that way. Blue photons have more energy than red photons. Aha, shorter wavelengths have more energy than longer wavelengths. The hotter the star, the shorter the wavelength at which it emits most strongly. That kind of makes sense, because a hotter star, it says, is giving off more energy, more energetic photons overall, in other words. The 15,000 Kelvin star is bluish in color because it's giving off light of pretty much all wavelengths. If you look in this narrow range that our eyes can see, it's giving off more blue light than it is red light, so it gives it a bluish color. For the red star, its peak in the visible part of the spectrum? What part of the spectrum is it? Is it ultraviolet or infrared? Infrared. It's at longer than red wavelengths. The peak's at infrared, but it does give off visible light, but it's giving off more red light than it is blue light, so it makes it a reddish color. The sun peaks in a yellow-green wavelength in the middle of the visible spectrum. It produces a more even spread at all wavelengths, and so that our eyes perceive that as essentially whitish in color. Sunlight is pretty much whitish in color. So, in other words, you can understand the idea, well, that different stars have different colors based on their temperature is explained by this graph here, and it's related to the idea of where the peak is, because if the peak is in the ultraviolet, the star is going to look bluish, because where you go back to the visible, there's more blue light than red light. If the peak is in the infrared, it's a cooler star, it's going to look reddish, because in the visible, there's more red light than there is blue light. And in between, you can get whitish, yellowish kind of stars, like the sun. And so that it ties to Wien's law that way. Okay, so any questions about that? That's kind of part one. And then there's the Stefan-Boltzmann law. Notice that a hotter black body is actually brighter in every wavelength than a cooler black body. The amount of energy coming out of each square meter of the 15,000 Kelvin star is bigger at every wavelength than is coming out of the 5,800 Kelvin star, and that's bigger at every wavelength than is coming out of the 3,000 Kelvin star per square meter. And so in other words, the flux, the power coming out of each square meter is related to the temperature, such that the higher the temperature, the more power is coming out of each square meter. That's described by the Stefan-Boltzmann law. The flux is sigma times the temperature to the fourth power. So hotter stars have more energy, by a lot, coming out of each square meter of their surfaces. And then tying that all together is the idea that we use to understand in detail what the positions of stars are telling us on the HR diagram. The luminosity will be the flux from the surface multiplied by the total area of the surface. unit-wise luminosity is watts, how many joules per second are coming out of the entire star. The flux is how many watts are coming out of each square meter. And the area is the total number of square meters. So the total number of watts is the number of watts coming out of each square meter times the total number of square meters. The flux times the area. Put another way, the luminosity is sigma t to the fourth power, that's our expression for the flux, and the area of the star, if it's spherical, is going to be 4 pi times its radius squared. That's the other way we looked at it. It's related to the surface temperature of the star and the radius of the star are tied in there as well. And then that's what we use to be able to understand, for example, just from their positions on the HR diagram, that a G spectral class giant star is bigger than a G spectral class main sequence star. We know that because the G spectral class giant star is higher up on the HR diagram, and so that tells us that since it has the same amount of energy per second coming out of each square meter, it must have more square meters. So for example, if we compare, say, Barnard's star to Mira, Mira has much more luminosity than Barnard's star, but it's about the same temperature. Since it's about the same temperature, the flux is the same, but Mira has a much higher luminosity, so it must have a much bigger area as well. It must be a bigger star in order to be so much more luminous for the same temperature. Yes?
How is the fact that the sky is dark at night evidence that the universe has an infinite age?
As
And
a-
it's consistent with the Big Bang Theory?
Yeah, so that's something that it's a little surprising at first. It doesn't seem, you're so used to you go out at night, it's dark, and so it's like, wow, that's actually telling us something profound about the universe. And the reason for that is, suppose that the universe was infinite in extent and had always been around, then that would mean that we could expect that if you look far enough, no matter what direction you look, your eventually line of sight would land on the surface of a star somewhere. It's like if you were in an infinite forest, then no matter where you look, you're eventually going to run into your line of sight's going to hit a tree trunk somewhere if you're in an infinite forest. So you would see tree trunk wherever you looked in an infinite forest. In an infinite universe where stars have been around forever, it's not changing with time, then no matter where you looked, eventually your line of sight will run into the surface of a star, and that would imply that everywhere you look should be ablaze with light. It should be as bright as the surface of a star in every direction. And yet, when we go out at night, this is not what we see. And so, what could explain that? One thing would be, well, what if the universe is not filled with stars out to infinity? What if there's only a finite region where there are stars in the universe? Well, then you'd have lines of sight which never hit a star, no matter how far you extended them. That's in fact the case, because the universe may well be infinite in extent, but it's changing over time. The further we look back into space, the more we're looking back. The further we look out into space, the farther we're looking back in time, right? Have stars always existed in the universe? No, there were no stars in the early universe. And so that means that if we look far enough out, we're looking to a time when there were no stars. And so as a result, it's not true that no matter what direction you point in, your line of sight eventually runs into a star. There's just not enough stars in the universe, and those stars have not been around forever. There's not enough stars in the visible part of the universe to always have our line of sight run into a star. Because when we look far enough out, we're looking back to when there weren't any stars. And that's why the sky is dark at night. Because if we look far enough out into space, we're looking back to when there was no stars. And so that means that you can have lines of sight that don't run into any stars because there aren't any stars in between us and those points that we're looking at.